Welcome back, everyone. So we're going to get into chapter 2, and that is going to bring us into a little bit of chemistry. So we're not going to go too deep into chemistry, but we do need a little bit of chemistry to understand the basics of biology. So this particular chapter is divided into three sections or themes. So we're going to start out by looking at elements and atoms and compounds. So if you recall from the previous chapter, we learned about life's hierarchy. And so we talked about the cell is made of organelles, and the organelles are made of molecules, and the molecules are made of atoms. So we're going to start out this chapter by looking at the smallest unit of matter, which are the atoms. And we're going to learn about them, and we'll eventually learn about how they form chemical bonds with each other to form molecules. And then we'll end the chapter learning about water, because water is essential for life. So let's start out by describing matter. So we already talked about how atoms are the smallest unit of matter, but we didn't really define what matter is. So matter is anything that takes up space and has mass. Okay, so basically everything around you is made of matter. Even the air that you breathe is made of matter, okay, because oxygen has mass. Maybe very small amount of mass, but it still has mass. So matter is everywhere. And we can break down our matter into atoms, which again are the smallest unit of matter. And atoms can be described by their chemical compounds or chemical elements, which are described in a periodic table. So if you've seen a periodic table, you can see all the description of the naturally occurring elements in our world. And so those are basically substances that cannot be broken down chemically to other substances. So think of, for example, oxygen. Oxygen is an element that cannot be broken down into something else. Hydrogen is an element that cannot be broken down into something else. So elements are those units of matter that cannot be broken down into anything. And a single unit of an element is called an atom. Okay. Now, if we take two or more elements in a fixed ratio, we call that a compound. Okay, so if we take, for example, Na, which is sodium, and Cl, which is chloride, we put them together with a chemical bond and we form sodium chloride. Okay. Another example is water. Okay, so H2O. Okay, so here we have a figure of water. We have one oxygen atom connected to two hydrogen atoms to form a water molecule. Now, if we look at our particular bodies, of course, are made of matter. And we can take a look at the majority of our body is made of just 4 elements of that matter. So we're mainly made of oxygen, carbon, hydrogen, and nitrogen. Okay, and you can see that oxygen is 65% of your body. So most of our body is just made of those 4 elements. Okay. And then about the rest, 4%, is calcium, potassium, phosphorus, and sulfur. So those make up pretty much the last 4%, okay? So, basically just 8 elements make up us. But we do have 25 essential elements that our body requires. So the rest of them are what we call trace elements. So trace elements are elements that we need in a minute quantity, okay? So examples would be like iron or iodine or boron or chromium or cobalt or copper, fluorine, manganese. You don't need to memorize, by the way, all of these abbreviations. I just have been teaching this class a lot of times, so I have them off the top of my head. But these are just some examples of trace elements that we just need in minute quantities. And if we're deficient in one of them, it can cause a lot of problems. So for example, this person over here has a goiter, okay? So that happens when your body lacks iodine. And iodine is something that's kind of hard to find in a normal diet. And so that's why our diet tends to be fortified with iodine. So for example, salt has iodide, a compound added to it to help supplement that minute trace element that we require to avoid getting goiters, which is something that happens with your thyroid. So here's just a brief overview of all of those elements. You only need to basically know the 4 main elements that make up your body, as well as just, think of some examples of trace elements. You don't need to memorize them all, okay? So about 96% of your body is made of just those 4: oxygen, carbon, hydrogen, and nitrogen, okay? The other 4% make up the rest, so calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. And then we have our trace elements. So even though we just need a very, very small amount, they are necessary. So if we're deficient in iron, for example, think about what happens. So a lot of women, for example, get iron deficiencies, and so that leads to anemia. Or somebody might have an iodine deficiency and end up with goiters. Okay, so those are some examples for you. And this is this table you can find in your textbook. All right, so let's get into those elemental properties, starting with an atom. So we already talked about in our life's hierarchy, the atom is basically that smallest level of life's hierarchy. So it's the smallest unit of an element. It's the smallest unit of matter. So we can take a look at an oxygen atom, or a nitrogen atom, or a calcium atom. So an atom is the smallest unit of an element. And atoms, they consist of 3 subatomic particles. So we have our protons, our neutrons, and our electrons. So the protons and the neutrons, they hang out in what's called the nucleus of the atom. And the protons being positively charged and the neutrons being a neutral charge. So they will be kind of together in the nucleus of that atom. And then surrounding the nucleus in what we call orbitals are the electrons with their negative charge, okay? So if you take a look here in our example, we have 2 protons. And so right away I know that that atom that we're looking at is an atom of helium, because helium always has 2 protons. Okay, so that helium atom has 2 protons, and it also has 2 neutrons in its center. And then it has 2 electrons circulating the orbit surrounding the nucleus. Okay, so that forms a helium atom. Now the reason why I know that helium has 2 protons is because that's its atomic number. So if we look at a periodic table, which we'll get a chance to look at in a little bit, periodic tables, they are sequenced by the elements, and they're categorized by the number of protons. So the number of protons is their atomic number, and that number never changes. So for example, hydrogen has 1 proton. It will always have 1 proton, so its atomic number is 1. Helium always has 2 protons, so its atomic number is 2. In this example, you can see sodium has 11 protons. So it will always have 11 protons. It will never have 10 protons, because if it had 10 protons, then it would be something else. It would be, I believe, neon. If it had 12 protons, then it would be something else, a different element. So the atomic number is the number of protons, and that never changes for the element. Okay. The other thing you'll notice in the periodic table, it will give you another number which we call the mass number. So the mass number is the number of protons and neutrons in that particular element. So you might be thinking, why don't we include electrons? Well, we do, but the electrons have such a small amount of mass that it's negligible in our calculations. So therefore, basically protons and neutrons are the only part of the atom that really has measurable mass. And so that's what we add up. So you can see here that our mass number for this particular sodium atom is 23. So if it's 23, we can figure out how many neutrons it has, because we know that sodium always has 11 protons. So how many neutrons will it have if the mass number is 23? Well, it must have 12 neutrons, because 12 plus 11 equals 23. Okay, so we can use that mass number to determine how many neutrons a particular atom has. Okay. Now, sometimes when we look at the periodic table, we will get a number that has a decimal point with some numbers after it. So that's what we call the atomic mass. So the atomic mass is basically the kind of average of all of the elements isotopes, and so it can be a little bit different. Okay, so for example, sodium, I think on the periodic table, I can't remember off the top of my head, but it might be like 23.45 or something like that. And so its atomic mass is basically just an average of all of its naturally occurring isotopes, which we haven't talked about. So what is an isotope? An isotope is basically an element that differs in the number of neutrons. Okay, so we can have isotopes that, they have the same number of protons for that particular element. They always have the same number of protons, but they can have different number of neutrons. So if you take a look here at our isotopes of carbon, we have carbon-12, carbon-13, and carbon-14. All of the carbons have 6 protons, okay, because that's its mass, that's its atomic number. That never changes. So the atomic number, if you look it up in a periodic table for carbon, is always going to be 6. But the number of neutrons will change. So carbon-12 has 6 neutrons, so that means its mass number is 12. So that's why we call it carbon-12. 6 plus 6 equals 12. Carbon-13 has an extra neutron, so it has 7 neutrons instead of 6, so its mass number is 13. Carbon-14 has 8 neutrons, so its mass number is 14. So you can see how carbon-13 and 14 are isotopes of carbon, because they have differing number of neutrons. Now, some of these isotopes are what we call radioactive isotopes. So what radioactive isotopes are basically they're isotopes that will decay or break down spontaneously, giving off particles and energy. So for example, some isotopes might be unstable, like carbon-14, for example, is an unstable atom, and so it will want to give off some particles to drop down to a more stable form. Okay, so it can actually give off neutrons Sometimes they can even give off protons and become a different element. All right. So the radioactive isotopes, they will decay spontaneously, and when they do that, they give off energy. So think about, if you've ever heard of, nuclear power plants, things like that. So those were using very unstable isotopes of uranium, and when the uranium, when it's giving off in that case, it's giving off a bunch of neutrons, it's releasing a bunch of energy in the process, and so we're harnessing that energy for electricity. We can also use it for other things. So we can do carbon dating for fossils. So we can figure out, what percentage of carbon-14 is in us today. So everybody has carbon-14 inside of you today in your living tissue. And then we can figure out how much percentage of that should be in a fossil and compare it to what's in a fossil. Okay, so because it has a half-life, so carbon-14 will decay. I forget what it decays down to. I don't think it's carbon-12. I don't remember off the top of my head. So we can use that and compare to the ratio of carbon-14 to the more stable form to see how old it is based on the half-life of that carbon. We can also use it to trace atoms through metabolic processes. So, for example, we can use things that have these half-lives, these radioactive half-lives that are really, really short, to be able to use them in metabolic processes, which are just basically chemical reactions in our body, to see if we have, for example, some sort of metabolic issue in our body, and that can be used to diagnose medical disorders. Okay, so for example, you can see here we have cancerous throat tissue, so that can be diagnosed with, well, usually like in the thyroid, which this looks like it's not quite in the thyroid, but in that area, they might do a radioactive isotope of iodine. So because your thyroid takes up iodine, so if it's radioactive, you can kind of see where in the thyroid is the metabolic process occurring more quickly. And so that can kind of isolate the area that might have, the non-working area versus the working area, and be able to diagnose a medical disorder. So isotopes, again, going back, they are just elements that have different number of neutrons. So here's a question for you. A nitrogen atom has 7 protons, and its most common isotope has 7 neutrons. A radioactive isotope of nitrogen has 9 neutrons. So what is the atomic number and mass number of this radioactive nitrogen? Well, first off, what's the atomic number of nitrogen? Remember, the atomic number equals the number of protons. So if nitrogen has 7 protons, its atomic number must be 7. Okay. Next, we need to figure out the mass number. Okay, so how do we figure out the mass number? We add the number of protons plus the number of neutrons. Okay, so for the isotope, we have 9 neutrons plus 7 protons. So what does that make the mass number? We have 16. And if you recall from a previous slide, the unit of measurement is in daltons, okay, or atomic mass units, depends on what you're looking at. Okay, so the mass number is 16 for that particular isotope. Okay, a common, the normal, most common isotope has 7 neutrons, so that would be mass number of 14. But the radioactive one has a mass number of 9, so it's mass number, or 9 neutrons, so it has a mass number of 16. Okay, So I like to include these, basically these flow charts to help us kind of bring together all the new terms that we're learning in a more visual format and this helps some of you, especially you visual learners out there, kind of comprehend things a little bit better. So at the top we have atoms, and then we have to fill in the blank. So atoms that are positively charged, what are those called? So what do we put in A? So that would be protons. And proton, the number present equals the atomic number of each element. Next we have atoms that have neutral, what are they called? That would be the neutrons. Okay, that subatomic particle. Neutrons, the number may differ in. So what do we call atoms that differ in the number of neutrons? Those are called isotopes. So D is isotope. And then the atoms, they have negatively charged, what are those subatomic particles called? Electrons. And the number in the outer shell determines the formation of the basically the chemical bonds, and we'll talk about that in the next section here. Okay. All right, so let's get into those electrons. So the electrons we know are circulating the nucleus of the atom, and they are circulating the atom in a particular form. So how the electrons are circulating the atom is basically in what we call electron shells. And we'll talk more about these shells and how many electrons each shell holds. But the outermost electron shell for that particular atom is what we call the valence shell. And that valence shell, if it's incomplete, meaning it doesn't have the maximum number of electrons that it can hold, is going to be reactive. So it's going to want to basically form chemical bonds with other atoms. So we're going to talk about these electron shells, and particularly the valence shell, and that will help us predict bonding patterns of different atoms, particularly different elements of atoms. So let's take a look. Here's an example of this is not really a periodic table, but it's set up like a periodic table where we have hydrogen over here, helium over here, and then you can see that the atomic number is present, but the atomic mass is not. Okay, well there's the atomic mass. So you can see helium, the atomic mass is 4.003. So it's basically most common. It's going to have 2 protons. How many neutrons? Most likely 2. Okay, and 2 electrons. Okay, so the rule of these orbitals or these shells, the first shell houses a maximum of 2 electrons. Okay, so it will never house more than 2. Okay, so the first shell always houses 2. The second shell can house a maximum of 8 electrons, as does the third shell. Okay, so the first shell can house maximum of 2 electrons. The second and third each can house a maximum of 8 electrons. So if we look at something like sodium, sodium has 11 electrons. So it will fill its first shell with 2 electrons. It will fill its second shell with 8 electrons. And then now it has 1 leftover electron to fill its third shell. And sodium in particular, it is going to be highly reactive because its valence shell only has 1 electron. And it wants to fill that its outermost shell. Okay. Most likely it's not going to gain 7 electrons though. Okay, so it's going to want to probably get rid of that extra electron and drop down to the second shell, and because that one is filled. Now if you look at something like chlorine, look at chlorine. Chlorine is got 17 protons, so it has 17 electrons in its stable form, or its neutral form. So the first 2 fill its first shell, the next 8 fill its second shell, and then it has 7 filling its third shell. So now it just needs 1 more electron to fill its outermost shell. So that's where that idea of chemical bonding comes in place, okay? Because chlorine just needs 1 electron to fill its outermost shell to be the most stable and happy. Sodium wants to get rid of that outermost electron and drop down to its second shell, which is already filled. So they could form a bond, okay, where, you know, sodium can donate its electron to chlorine and form a bond, okay? So that's where we can predict bonding with our different elements, okay? Now you'll notice the ones on the left, they're the ones that are going to be basically more likely going to want to lose electrons. The ones closer to the right, not the furthest right, the closer to the right, are going to want to gain electrons, okay? And then something like carbon in the middle, it basically has 4 electrons, so it's not going to gain or lose 4 electrons, so it's going to basically have to share electrons, and we'll talk about that chemical bonding in a bit. Now finally, before we move on, I just want to point out the far right. The far right, you might know already, those are called the noble gases, and they are always going to be stable because their electron shells are filled. And so they are going to be non-reactive. Okay, so helium does not want to bond with anybody because it's already, you know, happy in its own state. Okay, argon does not want to bond with anybody because its electron valence shell is already filled, so it doesn't really want to give up or share or get rid of any electrons. It already has what it wants. So the noble gases are the non-reactive elements, okay? But then something like fluorine and chlorine, the halogens, they're going to want to be reactive with maybe, you know, the first column here. Okay, so here's a checkpoint question for you. How many electrons and electron shells does a sodium atom have? How many electrons are in its valence shell? So let's answer the first question. How many electrons does sodium have? Now we automatically think the number of protons equals the number of electrons. So how many protons does sodium have? Well, if its atomic number is 11, then that means it has 11 protons. So that means it has 11 electrons. Okay, and we can actually count them. There's 11 there. And how many electron shells does it have? Well, it looks like there's 3 circles, so it has 3 shells. So how many electrons are in its valence shell? So remember, the valence shell is the outermost shell. So that answer would be 1. So it has 1 single electron in its outermost shell, the valence shell. Okay. All right. So as I stated before, if we look at the electron shells, we can kind of determine the bonding patterns of that particular atom, okay? So we know that electron shells, as they become filled, they become less reactive, okay? But we want to focus in on that outermost shell, the valence shell, and if it's not full, it's going to want to interact with other atoms. And there's different ways that it can interact with other atoms to form chemical bonds. Sometimes they'll share atoms. Okay, so something like carbon is not going to be able to lose all 4 electrons. It's not going to gain 4 electrons. So it's going to share electrons, and we'll talk more about that. Whereas something like chlorine, it just needs one electron to fill its outermost shell. It's most likely going to gain an electron. And when it gains an electron, it's going to have an extra electron orbiting because it'll fill its outermost shell. And so it has an odd number of electrons to protons, so it actually has more electrons than protons. So it will be negatively charged in that state because it has an extra electron. And we'll talk more about that, but this is called an ion. Okay. And then something like sodium will want to lose electrons, so it can drop down to its second shell. And if it loses electrons, then again, it has an abnormal number of electrons to protons. It actually has more protons than electrons, so it will be positively charged, and that's a different type of ion. So when these things share or gain or lose electrons, those attractions to other atoms we call chemical bonds. So we'll talk about the main types of chemical bonds. So chemical bonds form when atoms interact to complete their valence shell. So in this class, we're going to focus in on 3 types of chemical bonds. We're going to talk about covalent bonds, ionic bonds, and hydrogen bonds. Okay, so all 3 types. To start us out with chemical bonds, I'm going to show you this. It's called Crash Course, which is another one of those YouTube video collections that can be useful. So Crash Course, this is a chemistry video, but he also has a lot of biology videos. So you can use his sources as well as the Amoeba Sisters videos. But this one, it delves into the chemical bonds. So we're going to go through this. He'll describe the types of chemical bonds. Some of them will be a little bit more in depth than we need for this class, but that's okay. And then we'll describe them together in detail from the text.
Humans, like chemicals, are really all about bonds. Think about all the relationships in your life. You're a casual acquaintance to some people, a colleague or a friend to others, and maybe more to that someone special. Maybe you're dating someone casually, or you're in a committed relationship, or you're married. There are all kinds of different combinations of people out there. And sometimes, people fall for a vampire or a werewolf. Who am I to judge? Fact is, each type of relationship requires different things from you and the other person. But if you play your cards right, these relationships allow you to relax and escape the stresses that come with the constant search for affection. Distance is important in relationships too. Of course, too much distance makes it hard to stay focused on each other and requires a lot of effort to keep things together. And I may not have to tell you, too little distance can be a problem as well. Everyone needs their space, and when you don't have any, you just end up pushing away from whatever's crowding you. In this way, atoms are a lot like us. We call their relationships bonds, just like we do with our own relationships. And there are many different types. Each kind of atomic relationship requires a different type of energy, but they all do best when they settle into the lowest stress situation possible. The nature of the bond between atoms is related to the distance between them, and like people and vampires and werewolves, I suppose, it also depends on how positive or negative they are. The difference is that, unlike human relationships, we can analyze exactly what makes different kinds of chemical relationships work. And that's what this episode is all about. But people, please remember that we here at Crash Course do not dispense relationship advice. First things first, why do atoms do this at all? Well, like everything else in the universe, atoms do whatever they can to reduce their overall energy. And they reach their lowest energy by achieving a balance between attractive and repulsive forces, being neither too clingy nor too aloof. So when two atoms approach each other, the electrons of each are attracted to the protons of the other. This is the electrostatic force. Like charges repel, opposites attract. Like in real life, or at least Paula Abdul songs. I know, I'm old. So when one atom is attracted to another, just like Edward Cullen and Bella in chemistry class, to use a slightly more timely reference, it gets stressed out by the attractive force and tries to relieve the stress by getting closer. We've all been there, right? That hot, nerdy vampire girl in your chemistry class, it's intense. The pull is so strong that the stress level or energy rises when the two are separated, so they stay close. But sometimes they can get a little too close. When that happens, the nuclei repel each other because of their like charges, and the energy between them rapidly increases, and they both back off just enough to find that perfect little distance between them, and everyone relaxes. This ideal, wonderful distance is the bond length. It's the distance between two nuclei at the point of minimum energy. In other words, where the attractive and repulsive forces cancel each other out. The distance at which these two atoms of chlorine reach their minimum energy, caught between the attraction of the electrons to the nucleus and the protons repelling the nuclei, is the bond length. That energy minimum, which we know absolutely is negative 239 kilojoules per mole, occurs when the distance between the atoms is 0.00199 nanometers. That distance is the bond length of Cl2, chlorine gas. Now, because the electrons are attracted to both nuclei in the molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. As you know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativities of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one, like how all the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like hydrogen with an electronegativity of 2.1 and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many in fact that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their electrons so tightly that they're more likely to share them with another atom than to gain or lose them altogether. Metals, on the other hand, have loosely held outer electron shells, so they're constantly dropping electrons and becoming positive ions. And when positive ions come across negative ions, like those formed from halogens, for instance, you have to know what's going to happen. They are attracted to each other, which means energy is required to keep them apart, which means that they're gonna bond if they can, creating that oh-so-wonderful point of minimum energy. This type of bond is unsurprisingly called an ionic bond, a bond formed between a positive ion and a negative ion. Because the ions are formed when one atom loses electrons and the other gains them, we often say that an ionic bond is formed by the transfer of electrons from one atom to another. And we can calculate the amount of energy that exists in a bond between ions at a given distance using a formula called Coulomb's law. Note that this only works for ionic bonds because the calculation requires the charges of the ions, which covalent bonds don't have. Coulomb's law says that the energy between two ions equals the product of the two charges, which are represented by capital Q's, because why not, divided by the distance or radius between the two nuclei, all multiplied by a constant. 2.31 times 10 to the negative 19th joules per nanometer. Of course, the radius also has to be expressed in nanometers, you gotta make the units match. Let's see how it works with something simple, sodium chloride or table salt. We know that the normal charge on sodium ion is +1 and the normal charge on chloride is -1. These are Q1 and Q2. The length of a stable NaCl bond is 0.276 nanometers, so we put that in for the radius. And finally, a quick calculation tells us that the bond contains negative 8.37 times 10 to the negative 19th joules of energy. Remember that negative number represents a decrease in the energy of the system due to an attractive force, which certainly makes sense here. Sodium and chloride ions are strongly attracted to each other due to their opposite charges. Of course, you might have noticed that negative 8.37 times 10 to the negative 19th joules looks like a tiny, tiny number, but keep in mind we're talking about one single pair of ions. The negative 239 kilojoules that we got for chlorine, that was for a whole mole of molecules. When multiplied by the 10 to the 17th or so ions in a single grain of table salt, and then by the thousands of grains of salt in a mole, the energy becomes much more significant. The NaCl bond is in fact quite strong. And because they consist of a positive ion and a negative ion, two charges charges completely separated between two different particles, ionic bonds are extremely polar, way more polar than polar covalent bonds. And so those are our three types of bonds. Non-polar covalent, formed by the equal or nearly equal sharing of two electrons between nonmetal or metalloid atoms. Polar covalent, formed by the uneven sharing of electrons between two nonmetals or metalloids. And ionic, formed by the transfer of electrons from a metal to a nonmetal. It's important to remember, though, that there aren't only three designations for chemical bonds. Just like human relationships, bonds don't always have really well-defined boundaries. Everything is a continuum. Labels are useful, but they can only take us so far. There are, however, certain properties that each kind of bond tends to have that you should know. For instance, ionic compounds are often crystalline in their solid form because of the way the ions pack together, like salt is. They're generally soluble in water because the two ions interact separately with the positively and negatively charged areas on a water molecule, and once they're separated or dissolved, the ions allow the solution to conduct electricity. Covalent compounds, on the other hand, tend to be softer solids, liquids, or gases like Cl2 is at room temperature. They're often not soluble in water, and even when they are, the solutions don't conduct electricity. The difference in these properties stem mostly from the differences in their polarities. So yeah, polarity is crazy important. So important that we'll be doing a whole episode on it soon. Until then, I want to thank you for the bond that you have to Crash Course Chemistry, whether it's casual observer, faithful viewer, or committed subscriber. Today, if you were paying attention, you learned that chemical bonds form in order to minimize the energy between two atoms or ions. You've also learned that the chemical bonds may be covalent if atoms share electrons, and that covalent bonds can share those electrons evenly or unevenly. Bonds can also be ionic if the electrons are transferred, and you learned how to calculate the energy transferred in an ionic bond using Coulomb's law. This episode of Crash Course.
Okay, so from that video, yes, it went into a little bit more depth than we're going to need. We're not going to have to calculate any distances between atoms or anything like that. But it did talk about both the covalent bonds and the ionic bonds, though it didn't talk about the hydrogen bonds. But we'll get into detail of all three. So let's start with the ionic bond. So from the video, he talked about how we have the ions. You have a positively charged ion and a negatively charged ion that are going to be attracted to each other. And so, first of all, an ion is when an atom wants to either gain an electron or lose an electron. So when it gains the electron, it's going to have an extra electron to its protons, and so it will have a negative charge. And so when it's charged, either negative or positive, doesn't matter which, it's called an ion. And specifically, a positively charged ion is called a cation, and a negatively charged ion is called an anion. So when we have a positively charged ion, such as sodium, and a negatively charged ion, such as chlorine, they're going to want to form that bond together by donating the sodium, donating its electron to the chlorine. That's going to form an ionic bond. So ionic bond is that attraction between two oppositely charged ions. Now from the video, Hank said that it was a strong bond, but relatively to the other two bond, or to the covalent bond, it's weaker. Okay, so covalent bonds are going to be a lot stronger than ionic bonds. So ionic bonds we consider a weaker bond. Okay, so you can see here we have our sodium donating or losing an electron to chlorine. And by doing so, it becomes a cation, the chlorine becomes an anion, and they're forming an ionic bond, which forms something called sodium chloride or table salt. Okay, so when we've talked about compounds already. So compounds are two elements of fixed ratio. When we have two or more atoms held together by bonds, we call those molecules. So we're going to talk about the molecular bonds that form between ions, okay, so ionic bonds. We'll also talk about those covalent bonds where they share electrons. And then hydrogen bonds, you can kind of guess already, is between a hydrogen atom and something else. So let's talk about those ionic bonds. So we already talked that we have a positively charged cation and a negatively charged anion. And they come together to form an ionic bond. So their attraction to the positive and negative between them form that ionic bond. And in particular, when we form ionic bond, these are at fixed ratios, so they are both molecules and compounds because we have equal amounts of sodium to chloride in this particular chunk of salt here. And basically these ionic bonds or ionic compounds, they're also known as salts. Okay, so the salts. And from the video, he talked about how metals reacting with non-metals. But for biology, since we don't really talk about metals in our bodies, because it's such a minute amount, it's more of the first or second columns in our periodic table reacting with the second to last column, the halogens. Okay. So we're going to watch a video produced by your textbook that just kind of goes over what we talked about here.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay. So that was just kind of a review of what we've talked about with cations and anions forming those ionic bonds. So let's get into the second type of chemical bonding, the covalent bond. So covalent bond is when we share electrons. Okay, so instead of giving or taking an electron, they're going to actually share electrons in their orbits. And this type of bond is a strong bond, so it's going to be stronger than ionic bonds. Now, in this picture over here, we have 2 hydrogen atoms. And if you recall, the atomic number of hydrogen is 1, so it will have 1 electron. But how many electrons does it want to have? So it wants to fill its outermost shell, in this case, the first shell. So it wants a total of 2 electrons. And so in this case, if we have 2 hydrogen atoms, they can share each other's electrons to fill their outermost shells. Okay, so if they're sharing the electrons, they form a strong bond. Okay, so they're not going to want to break apart because then, the other's electron goes with it. And so it doesn't have its outermost shell filled. So covalent bonds are very, very strong. Okay, now you might be thinking, okay, well, are the electrons just sitting right here in the middle? Now remember, the electrons are always constantly moving. So, they're circulating around each of the atoms. Okay, so the extra electron might be, circulating each one evenly in this case. Okay, now sometimes, in this case, we have the 2 atoms here are sharing a pair of electrons, so that's what we call a single bond. And we usually denote that with just 1 bar between the 2 elements symbols. Occasionally you'll see, for example, oxygen. If we have 2 oxygen atoms sharing electrons, they can actually share 2 pairs of electrons between each other. to fill their outermost shell, because oxygen, its atomic number is 8. So in its first shell, it's going to be 2, and its second shell, it's going to be 6. So it just needs 2 more electrons to fill its outermost shell. So if the 2 oxygen atoms share those extra electrons, 2 pairs of their electrons, then they form a double bond together. Okay, so that's denoted by those 2 lines in between the element symbols. Okay, so covalent bonds share electrons and they're very strong. And then just remember that molecules, they consist of 2 or more covalently bonded atoms. So here's just some example of different covalent bonds. So we talked about the hydrogen bond where we have a single pair of electrons being shared. Okay, so we just see that single line there. Oxygen, they have 2 pairs of electrons being shared. So you can see here's one pair, here's another pair. So that's why we have that double bond noted here. In water, remember oxygen has 6 electrons in its valence shell, hydrogen has 1. So if we have 2 hydrogens bonded to oxygen, that will fill the outermost shells of all 3 of these atoms. Okay, so that's forming H2O. You can see how we write it out in the structural formula. And then methane has basically one carbon and 4 hydrogens. In this case, remember carbon just has 4 electrons in its valence shell, so it's going to form up to 4 bonds. So in this case, it has 4 bonds with hydrogens. Okay. Now in the video, Hank talked about electronegativity. So electronegativity is an atom's attraction for the electrons of the covalent bond. Now, it's dependent on the particular element. So he talked about how oxygen, its electronegativity is about 3.5, whereas I think hydrogen was, 2.1. So there's unevenness there. So because oxygen has a higher electronegativity, it's going to be more attractive for the electrons. And again, remember how those electrons, they're constantly circulating. Okay, so the hydrogen's electrons, it's going to be circulating, but sometimes it's going to be, moving into the oxygen's orbit because they're sharing the electrons. Same with the oxygen, it's going to be hanging out here. Less likely the oxygen's electron might make it to the hydrogen's orbit. It's because of its high electronegativity. And so because of that, since the oxygen, the electrons are more likely to be in its outermost orbit more often than the hydrogens, it's going to have a slightly negative charge on this side of the water molecule. And so that's what this symbol means. It means partial, so partially negative. So there's going to be a partially negative charge on this side of the molecule. Whereas on these sides of where the hydrogens are, there's going to be a partially positive charge because hydrogen's electron might actually end up circulating in the oxygens occasionally, okay? Because of that oxygen's negativity. And when that happens, we form a polar covalent bond. Sorry about that. Polar covalent bond. So polar covalent bond, polarity is when we have that unequal sharing of electrons. Okay, where we have one atom is more electronegative, and so there's an unequal sharing of electrons. So think of water molecules as the perfect example of a polar covalent bond between the oxygen and the hydrogen. When we don't have the electronegativity unevenness, if the 2 atoms have similar electronegativities, they're going to share the electrons equally. So that forms a non-polar covalent bond, okay, where we don't have the unequal sharing. Okay, so non-polar, think equal sharing of electrons. Polar, think unequal sharing of electrons. Okay, so if we look at our distribution again, we can see that hydrogen, H2, that is considered a non-polar covalent bond because they're equally sharing the electrons. Same with O2, oxygen with this oxygen molecule. It's sharing the electrons evenly, so this is a non-polar covalent bond. Methane, we have CH4. They're equally sharing the electrons, so this is a non-polar covalent bond. Here we have water, okay, and you can see how it's more bent, where we have, the hydrogens over here, and then we have the oxygen being more negative on one side, slightly negative, slightly positive on the other side. So that's an example of a polar covalent bond. Right? So let's watch a video to make sure we're understanding everything.
A covalent bond is the sharing of a pair of outer shell electrons by two atoms. For example, each of these hydrogen atoms has one electron in its outer shell, but needs two electrons to complete its outer shell. If the two hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as two or more atoms held together by covalent bonds. An oxygen atom needs two electrons to complete its outer shell. Two oxygen atoms can share two pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, two shared pairs of electrons. A carbon atom needs four electrons to complete its outer shell. It can share electrons with four hydrogen atoms, forming a methane molecule containing four single covalent bonds. Methane is a compound, a substance formed by the combination of two or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs two additional electrons to fill its outer shell. Thus it can form two single covalent bonds. An oxygen atom can share electrons with two hydrogen atoms, forming a molecule of water containing two single covalent bonds.
Okay, so that was a good visual, especially how you can see where the electrons are coming in. Okay. So let's do a checkpoint question to make sure we're understanding things. So looking at the electron distribution diagrams for hydrogen, oxygen, nitrogen, and carbon, which are kind of highlighted here in the figure, how many covalent bonds can each form? So let's start out with hydrogen. How many covalent bonds can hydrogen form? Well, it has one electron, so it can form one covalent bond. What about carbon? So we're looking at its second shell. And how many valence electrons does it have? So it has 4 valence electrons. So it can bond with up to 4 other atoms. Okay, so it can form as many as 4 covalent bonds. Okay. What about nitrogen? So nitrogen, it has 5 electrons in its valence shell. So how many covalent bonds can it form? If you said 3, I would agree with you, okay? So it needs 3 electrons. So it can bond with up to 3 other atoms to gain those 3 electrons. Now what about oxygen? How many covalent bonds can it form? Well, we already know that it can form 2 with hydrogens, right, to form water. So it has 6 valence electrons, so it wants to gain 2 electrons to fill its outermost shell, so it will want to bond with 2 atoms at most. So to form, it can bond with another oxygen, that's just one single atom, to form a double bond. or it can bond with something like 2 hydrogens, so it can form 2 covalent bonds. Okay, so we have 1 for hydrogen, 4 for carbon, 3 for nitrogen, and 2 for oxygen. All right, we're going to talk about our last chemical bond, which the crash course video did not talk about, and that is the hydrogen bond. So the hydrogen bond is a very weak bond, and it is a bond that occurs when we have a hydrogen atom that has a slightly partial positive charge that's going to be attracted to an electronegative atom from another molecule. Okay, so it's going to form a very weak hydrogen bond between the two. So here we have our oxygen, our water molecule, and remember the water molecule, it's held together by a polar covalent bond, so that hydrogen's not going to go anywhere. It's always going to be bonded to this oxygen here. But because the end of the hydrogen forms a partially positive charge, it's going to be attracted to the negative, partial negative of this ammonia molecule, excuse me. And so it's going to form a temporary hydrogen bond, okay? Now that's a very weak bond. It's going to be, forming with the ammonia molecule here. It's not going to break off and add itself to the ammonia molecule. So it's still held together really strongly with that covalent bond to the oxygen, but it will form a weak bond as well with the ammonia molecule to form a hydrogen bond. Okay, so these are weak bonds that form between a partially positive charged hydrogen and some sort of electronegative atom of a nearby molecule. Okay. So let's watch a video. We're going to talk about water, the water structure.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Okay, so from that video, we not only solidified that water itself is held together by a polar covalent bond, but we also saw that hydrogen with its partially positive end is going to be attracted to the partially negative end of a nearby molecule to form a hydrogen bond, which is a weak bond. Okay, so we're going to talk more about water, the properties of water coming up here. Okay, but before that, let's do a checkpoint question. What enables neighboring water molecules to hydrogen bond to one another? So if we have 2 water molecules nearby, what enables them to hydrogen bond to one another? Well, remember that the water molecule itself is polar. Okay, so there is a partially negative end, the oxygen end, and a partially positive end, the hydrogen end. And so because of that polarity, The partially positive hydrogen is going to be attracted to a partially negative end of a nearby water molecule to form hydrogen bond. So what enables the neighboring water molecules is its polarity. All right, here's another question for you. Based on the periodic table below and what you know about ions forming, which elements will most likely form an ionic bond? Would it be sodium and chlorine, carbon and oxygen, nitrogen and oxygen, silicon and chlorine, or will it be hydrogen and hydrogen? Which one will most likely form an ionic bond? So remember, the first column and the second to last are most likely forming ionic bonds. Okay, so sodium and chlorine would be a good answer. Okay, carbon and oxygen, they're too far apart. Nitrogen and oxygen, they're too close together. Silicon and chlorine, they're they're pretty different areas there. Hydrogen, same side. So the only one that would form an ionic bond would be A. Okay. Which ones would form covalent bonds? Well, pretty much all the rest, right? So carbon and oxygen, they can form a covalent bond. Okay, they can form like carbon monoxide, CO, or carbon dioxide, CO2. Nitrogen, oxygen can form nitrous oxide, I believe it is. Silicon and chlorine can form a covalent bond. Hydrogen and hydrogen can form covalent bonds. So basically all the rest can form a covalent bond with each other. The only exception is sodium and chlorine do not. All right, so we're going to get into the last section of chapter 2, which gets into the properties of water. So we already know that water is essential for life, but we don't know why. Well, one of the reasons is because of that hydrogen bond. So we talked about how that hydrogen bond, due to the water molecule's polarity, is going to be forming between nearby water molecules. And that allows for water to be so fluid in its liquid form. Okay, because those hydrogen bonds are constantly breaking and reforming between other nearby water molecules. And that's what makes water liquid at room temperature. Okay. It also, as the video described, because those bonds form and break constantly, they have that ability to store energy. Okay, so that's going to basically keep the temperature pretty stable, and along with other properties that we're going to talk about. So we're going to start out with an Amoeba Sisters video. So this will kind of go over the properties of water, and then we'll describe in detail those properties.
So we have a riddle for you. Okay, not really a riddle. We're bad at riddles, but more like clues about our favorite molecule. It's polar, it's shaped like an outstretched V, its properties are awesome, and it makes up 3/4 of the surface of the Earth. That one always gives it away. Our favorite molecule is water, and we're not going to lecture you about how important water is and the fact that all life as we know it could not survive without it, because, yeah, that's true. But we really want to talk about what makes water so unique for biology itself. What are some awesome properties of water? Now, we mentioned the shape of water and the fact that water is polar. It has one very electronegative oxygen that is always trying to keep the electrons closer to it than to the hydrogens it's bonded to. And this actually gives oxygen a slightly negative charge because of the electrons that are spending more time next to it. And it gives the hydrogens a slightly positive charge. Well, that means that other water molecules have an easy time bonding together. Why? Well, because the hydrogen of one water molecule with its slightly positive charge can bond to another water molecule's oxygen with that slightly negative charge. These bonds among the water molecules are hydrogen bonds, and these are the very bonds that allow water to have many of the properties that we're about to talk about. Have you ever looked at a really tall tree and wondered, how does the water get all the way up there? I mean, it's got to go against gravity. Gravity? Well, in our plant video, we talk about the xylem. It's vessels within certain types of plants, like trees, and these vessels transport water. But what's really neat about water is that it sticks to the xylem walls in what is known as adhesion, and this helps fight gravity. But water molecules, with their hydrogen bonding, they also bond to each other in something called cohesion. It's almost a beads on a string kind of fashion. Water molecules evaporate from a leaf, and then the next water molecule in line is pulled upwards, and so on. This cohesion is really a big deal. Cohesion is also a reason that water striders, one of our favorite insect types, can skate on water. Cohesion contributes to the surface tension of water. Water actually has quite a bit of surface tension compared to many other liquids. And it's not just water striders that can walk on water. There are a lot of insects, spiders, and even larger animals like reptiles and some birds that have the ability to walk on water. So, to the Google for that. Now, with water being polar, it's also a very powerful solvent for other molecules. And that means that water can dissolve many other molecules, especially polar molecules and ionic compounds. Now, why does that matter? Well, this is really important because many of the processes that occur in organisms use water as a solvent. In our body system video, we talk about the function of kidneys, and you definitely couldn't have kidneys doing their function without water. Also, a main component for body fluids is water. I'll never forget when I was little, my father built us a pond. We had some goldfish in there, and I loved this pond. Well, in West Texas, where we're from, it can freeze in the winter. And one morning, I went outside, terrified to find that the top of the pond had frozen. And I thought our fish were goners. Only to find out that they were swimming and doing their fish activities under the ice layer. It's common for many substances to actually contract when they freeze and to become more dense. But water expands when it freezes and becomes less dense in its frozen state, resulting in floating ice, where it can actually make this insulated surface layer that makes a difference for many organisms underneath. And this is due to the hydrogen bonds. See, at freezing level, the making and breaking of hydrogen bonds, which usually happens pretty often, it's not happening very much when frozen. And so the molecules, they're set into this lattice of hydrogen bonded molecules, just far enough apart that it's less dense in ice form than it is in water form. And that's going to be very important for all of that aquatic life. Speaking of temperature, water resists changing its temperature. It has what's called a high specific heat. Specific heat, it's a measurement of heat that's needed to be absorbed or lost for 1 gram of a substance to change its temperature by 1 degree Celsius. And that's why on the first day that school's out in the summer, it may be super hot outside, but the water could still be pretty cool. It's really good that water's like this for life. It's stabilizing for aquatic environment temperatures. And it also means that water can absorb a lot of heat in the summer without reaching as high of a temperature itself, which is useful when winter comes along, because then the water can release heat as it cools in the winter. This also impacts the environment. Now, still on the topic of temperature, consider evaporation. Many animals rely on evaporation to cool them. Think of water molecules. They are moving, but those that have more heat energy, they are moving the fastest. And they're the more likely molecules to make the phase change to gas. And these molecules, as they leave, their energy, their heat, is no longer on your skin. And by the way, all of this is not just animals too. Plants use evaporative cooling to aid them in hot temperatures. Excessive high temperatures could be very dangerous for many different processes in both plants and animals. It can be damaging to the enzymes involved in those processes. So, that evaporative cooling is very important. Well, we went through a lot of features of water. Definitely something to consider next time you encounter it, which, based on how much we depend on water, will likely be soon. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.
Right, so again, that video gave us a good overview of the properties of water, but we're going to go through each of them carefully. All right, so let's talk about one of the properties of water. So again, that water is a universal solvent. So because of its polarity, it's going to have that electronegative end on the oxygen side and the electropositive, partial positive end on the hydrogen side. And because of that, it's going to allow things to dissolve. And so being a solvent is a dissolving agent in a solution, whereas a solute is what is being dissolved. And so if we have something like water and we put something like salt in that water, the salt is going to dissolve. Okay, so think about salt. It's held together with an ionic bond. And the sodium, that is, in that case, a cation, that cation being partially positive is going to be attracted to the it's going to be positive. It's going to be attracted to the negative end of a water molecule. Okay, so it's going to break that ionic bond with the chlorine. The chlorine being an anion, is going to be attracted to the partially positive end of hydrogen, of the water molecule's hydrogen ends. And so they're going to, the water molecules are going to surround the chlorine anions and the sodium cations. And by doing so, that breaks the bond. And so now it's completely dissolved. So if we took that table salt and left it there, come back an hour later, it wouldn't be there, right? It would be all dissolved in that water. Okay, so water is a universal solvent because of its polarity and its ability to form hydrogen bonds. Okay, and then basically it just says an aqueous solution is one in which water is the solvent. So here we have an aqueous solution with salt and water. So here's a checkpoint question for you. Why are blood and most other biological fluids classified as aqueous solutions? Well, again, what's an aqueous solution? An aqueous solution is where the solvent is water. So our blood, if we think about it, blood is mainly water. It's just a bunch of water. If you ever looked at blood under a microscope, we have little blood cells, the red blood cells and the white blood cells, but it's carried in plasma, which is basically water and some other substances. Okay, so water is the solvent. So water is the solvent of life. Okay, so the solution, again, consisting of 2 or more substances, where we have the solvent, in this case being water, is the dissolving agent due to its polarity, and the solutes, typically being either charged atoms such as our chlorine and our sodium, or it could be a polar substance. So it doesn't necessarily have to be a charged ions. We can also have polar molecules can be dissolved in our universal solvent, the water, as well. And they form those aqueous solutions. Okay. We also have properties of water. We're going to talk about acids and bases. Now, you've probably heard about acids and bases. Okay, so certain things are acidic, certain things are basic, but you might not know what that means. Well, when we have, basically, if we have a water molecule, and we have actually two water molecules, and they actually undergo a reaction. In this case, it's an actual chemical reaction. It's just not like a hydrogen bond, but it's a chemical reaction where we have one hydrogen breaks off and attaches to the nearby oxygen. We form notice the charge. So this is going to be a cation, which we called hydronium. So hydronium is a cation. Hydroxide, OH negative, is an anion. So in this case, in the solution, we have hydroxide and hydronium. Okay. In doing so, basically the amount of positively charged hydrogens in water will make a solution more acidic. Okay, if we have less hydrogen ions floating around and more hydroxide ions in the solution, we end up with a basic solution. Okay, so that's how we tell the difference between acids and bases. So acids increase the hydrogen ion concentration in the water, whereas bases reduce it. So if we look over here, if we have an acidic solution, it's basically just a ratio. We're looking at more hydrogen ions to hydroxyl ions. And that's what makes it acidic. Okay? If it's basic, it's the opposite. It has less hydrogen ions to hydroxyl ions. And then neutral will be equal. We have equal amounts of hydrogen ions to hydroxyl ions. All right? So something like HCl. HCl is a strong acid. So when we put HCl in water, we form an acidic solution because that H will break off to form hydrogen ions and the chlorine will break off to form the chlorine. But now we have a bunch of hydrogen ions floating around. Okay, so that hydrogen ions will make an acidic solution. NaOH, if it's added to water, it will form a strong base, a basic solution, because all of those OHs that break off will be added to the solution, forming this more basic solution. Right? So acids have higher amounts of hydrogen concentration. Bases have lower concentration of hydrogen. Okay. Now some of you are familiar with the pH range. Okay, so we have a pH scale that goes from 0 to 14, where 7 is neutral. So remember, neutral means equal number of hydrogens to hydroxyl. If we have more hydrogens than hydroxyl, we have an acid, which is less than 7. If we have more hydroxyl to hydrogen, it's considered a base, which is greater than 7. All right. So you can see some common household products and bodily, liquids that and their corresponding pH. So something like, our pure water, that's going to be neutral. But human blood is very close to that. It's actually about 7.35 to 7.45 is its pH. So it's slightly basic or alkaline, but it's pretty much very close to 7. And same with saliva. Whereas something like household ammonia, that's going to be a strong base. Okay, so it's going to be, right around 11, 12. So there's going to be a lot more hydroxyl ions in that solution compared to hydrogens. Okay. Basically the gastric juice, so the gastric secretions in your stomach has a pH of 2. So that is a pretty strong acid. Okay. Now, another thing that you'll need to know with our pH scale is that it's a logarithmic scale. Okay, so that means that as we go up or down the scale, we're increasing or decreasing the concentration of hydrogens by a factor of 10. So for example, if we're comparing seawater with a pH of 8 to pure water, pH of 7, pure water has 10 times more hydrogen ions than seawater. Not 1, but 10. Okay, so as we move up or down the scale, we're moving by a factor of 10. If we're comparing black coffee, that's 5, to pure water, that's 7, black coffee has 10 times 10 or 100 times more hydrogen ions than pure water. So every time you move up or down, it's by a factor of 10, and you have to multiply it. So 10 times 10 equals 100. Okay, so if we're moving 3 spots, that's 10 times 10 times 10, or 1,000. All right. So just remember that it's a logarithmic scale. So each time you move a space, a number is a factor of 10. You're multiplying by 10. If you're moving 2 spaces, that's 10 times 10. 3 spaces, 10 times 10 times 10. All right. So here's a checkpoint question. Compared to the basic solution of pH 9, the same volume of an acidic solution at pH 4 has how many times more hydrogen? Well, let's see. So we go from 9 to 8, that's 10. 8 to 7, that's 10. 7 to 6, that's 10. 6 to 5, that's 10. 5 to 4, that's 10. So it's 10 times 10 times 10 times 10 times 10. So how many 10s are we doing? 1, 2, 3, 4, 5. So it's 10 to the 5th. Okay? So what would that be? So it would be basically a 1 with 5 zeros after it. So 100,000. So 10, here's, times 10, that's 100, times 10, that's 1,000, times 10, that's 10,000, times 10, that's 100,000. So if we're going from 9 to 4, that's 100,000 times more hydrogen ions that something like tomato juice has compared to pH 9. All right, here's another checkpoint question. Water has special properties including high cohesion, high surface tension, and the ability to absorb large amounts of heat per unit of mass. What kind of bond between water molecules gives water these special properties? Is it strong ionic bonds? Is it non-polar covalent bonds? Is it polar covalent bonds? Is it hydrogen bonds? Or is it weak ionic bonds? If you chose D, hydrogen bonds, I would agree with you. Okay, so in this case it says what kind of bonds between water molecules? That would be a hydrogen bond. If it's within a hydrogen or within a water molecule, it would be a polar covalent bond. But this is between. Remember, hydrogen bonds, they are going to allow cohesion. So cohesion is when we have water molecules sticking together with those hydrogen bonds, creating surface tension, and the ability to absorb large amounts of heat. Okay. All right, so let's see if we can put it all together in this visual here. So chemical bonds, we have chemical bonds, we have electron transfer between atoms creates ions. The attraction between ions creates what? What type of bond is that? That would be an ionic bond. So F is ionic bond. When we have chemical bonds where electrons sharing between atoms, electrons are shared, that's what type of bond? That would be a covalent bond. If it's an equal sharing, it's a non-covalent bond. If it's unequal sharing, what type of bond? A polar covalent. So a polar covalent bond, an example would be water. Water has important qualities due to polarity, and what's that bond between the hydrogen of one water molecule and the oxygen of another? That's a hydrogen bond. All right. So hopefully by now you have a good idea of the 3 types of bonds as well as the properties of water that will get you through chapter 2. Okay, so this concludes our first week of lectures. So by now you should be able to have, be able to review the textbook as well as answer all the assignments and quizzes this week.